Wait.
Yeah.
All right, let me get started. So thanks everyone for coming to MagNet Challenge 2, tutorial 5. After one summer, I hope many of you still remember MagNet Challenge and are making good progress. And as organizing committee, we feel like it's necessary for us to bring up our activity level a little bit before everyone feels like it's too late. So that's why the purpose of organizing this tutorial, and also to answer any questions you may have and clarify some of the final evaluation rules that we are deciding to take, and answer any questions that you may have. So for the audiences, if you have any question, any comments, feel free to raise your hand or type your questions in the Q&A, and we'll be very happy to answer those questions. So we'll run this in a more sort of like relaxed mode, so we can better interact with each other. And Shukai, go ahead.
Sure. Thank you. So today we're going to talk about tutorial 5, and thank you everybody for attending. Everyone can hear me all right, correct?
Yeah, it's
Yep,
okay.
perfect. Awesome. Great. So let's get started. So as we mentioned from the past 4 tutorials, right, the goal of this MagNet challenge is for you to produce or figure out some type of model that you have developed in the past few months and be able to apply it into this competition. So by this time, perhaps you should be able to figure out some preliminary models that you have developed for each materials. And this model may be in the form of a function that takes in the inputs of B, H, and gives you, given the next step B, and perhaps gives you the next step H, right? So because we want this to be autoregressive. And so at this point, the teams should have some sort of function that's able to produce this, right? And to, as a refresher, that if given a arbitrary sequence that we're provided here, right, you're usually provided with some B excitations, right? And then you're given some H excitations, maybe 0%, maybe some information, and you're asked that given that future excitation, what is my future output, right? So your function should be able to perform something similar to this to give you that next step or next few steps of output. So given this, right, we have come up with our pre-evaluation rules, which will also be carried into our final evaluation rules. So the pre-evaluation really for us is to see if every team is familiarized with the rules and are able to perform the competition into the final evaluation round. So first, let's talk about the data format that we're going to provide to you guys. So for pre-evaluation, we are going to provide you guys with the 10 materials of an example test data set of this first 10 materials that you guys already have, the data you guys already have. So these 10 materials, since you already have the data, right, it's really a self-evaluation to see if you're familiarized with the rules. And because for the finals, we're going to provide 5 unknown material with limited data, and we're going to test you on the data you haven't seen, right? So being able to perform the pre-evaluation will be very crucial as to perform the final evaluation. So for the pre-evaluation, we have provided each team with the 10 materials data, and each material has data set that looks something like the one seen here. As for example, for the BH sequences, instead of providing arbitrary or providing a full length data sequence, we're only providing 1,000 steps, right? And these 1,000 steps are randomly selected across many different sequences, many different temperatures and frequencies, and they are completely randomized so that your model should be able to just see a portion of it to predict the future portion. So in this case, the first thing we have to emphasize is that for this MagNet challenge, our sampling frequency is fixed. So you do not have to adapt your model to different sampling frequency. That is not part of our evaluation criteria. Now, with that being said, the data we give you guys are split into three different forms. The first form is that we're only providing 10% of the available H data and asking you, the teams, to use your function and predict that 90% of the unknown data time steps. And we also have the 50% to predict 50%. And then we also have the 90% to predict the 10%. So all in all, you will have three different types of data length for your H's that your model will need to adapt to give you that full prediction. And so for each material that we provided, we have a minimum of around 4,500 total segments for each material. So you will have plenty of segments you will need your model to test on.
You don't need to test on all 10 material,
Right.
only 2 materials.
Right.
And in fact, you don't have to do anything. If you don't want to do anything, you don't have to do anything. But we'll be happy to see if you can try your already trained methods and models on 2 materials, so that you know how. So you sort of like finish the entire process, and then be ready for the final test of the 5 new material.
Yes. Yes. So great. So once we give you the data, right, and you provide yourself with the model you have, and then you evaluate it, how do we evaluate your model? So we evaluate your model based on 2 criteria. Obviously, the first one is a sequence relative error, which is very obvious that since you're predicting an H sequence, and we would like to compare that with the measurement data that we provided so that you can have a sense of how close your sequence fits to that characteristic response of your actual material, right? Which is provided in the form of the measurement data. So in our sequence relative error, this one obviously is going to give us a sense of how well your prediction in your model is performing in terms of this autoregressive prediction. And so here, in all of the values that you need to calculate, the H measurement is already provided in our data set, right? And the H predict is the prediction that you are going to perform, which was seen in these yellow output unknown colors, right? So these are the prediction that you would need to perform. And you're comparing that with the measurement, which is provided in a separate file here. So given that, you should be able to get yourself a sequence relative error as long as your model is able to give you that H predict here. But giving just a sequence relative error, it's not really enough because in this case, you may have a sequence that fits the measurement really well, but that doesn't mean your phase shift with respect to B is necessarily correct in where that core loss comes into play. So we also added the second evaluation criteria, which is a normalized energy relative error. And now in this case, first we're calculating the measure of the predicted. We're calculating a predicted energy for this entire segment you predicted. So let's say if you're given 10% data and you predict 90%, you are calculating the energy for that 90% unknown. And then 50%, you're only calculating for the 50%, right? And then so given that, we are calculating the integral of dB dt times that predicted H, right? So that predicted H is again predicted using your model, and dB dt can easily be calculated using that B excitation we provided to you guys. And you then subtract that against the measurement energy. And all in all, you normalize that against the entire overall core loss, which is, in this case, the full length sequence. So here we only provide you with 1,000 steps, but each one of these 1,000 step segments is part of a full quasi-steady state sequence. So this core loss that we're talking about here is that loss, the total energy of that full length quasi-steady state sequence. And this way, we can have a good sense of whether your loss, your energy makes sense in terms of when you evaluate that against this specific material. So here you can see that for our time steps, the T0 is the beginning of the full sequence, and T3 is the end of the entire sequence, right? And then T1, T2 are simply the part of the time steps within the segment, which I'll show in the next slide here. So here for the core loss of the full sequences, you guys do not have the information of that. We provide that in our in your data set that we're providing to you guys.
So it's basically predicted core loss energy minus real core loss energy for the cycle you're predicting, normalized to the core loss energy of the total sequence.
That's
So
correct.
that's what we're doing here. So for the pretest, like before November 15th, you can play with it and then try your model on it and even train your model better for these two metrics. And in the final evaluation, of course, the measurement data, we are not releasing it. We're not releasing it. It's us. So we will be doing this evaluation. And of course, after the competition, we'll release all data we used for the test.
Yes. Great. So once you know the evaluation criteria, you will need to know what we are providing to you guys specifically. So here, for the data we provide to you guys, there are two H5 data files that we provide here for each material. The first one is called the material testing true. True in terms of the that every single data we provide in this data set is the full measurement data. So as you can see here, if we have an example of a full length sequence from 1 to n here, right, we are providing you guys with the entire B excitation sequence, and we're providing you with the full H measurement sequence as well. And so therefore you can calculate that core loss using simply going from when time is 1 all the way to time to n. So you can actually be able to calculate that core loss yourself as well. But we provide you guys with the core loss anyways, and each segment will have its respective temperature, which we'll also provide. And the second file is the material testing padded. Now, in this case, we actually also provided you guys with the same information of B, core loss, and temperature, just as a fact check to make sure that each file is synchronized. But the one thing that is different is that in this case, our H of T is no longer the full measurement sequence. In this case, we're provided you guys with some of them with, for example, 10% of the past known information, and then 90% of the predicted. And then some of them we provide with 90% known and 10% predicted. But all in all, the data we provide you guys will have 3 scenarios ranging from 10%, 50%, and 90%. So the testing padded is the one where you will use for the H sequence for your model to use that known information to predict that unknown. And then you use that predicted value to compare with the measurement H, which is shown in the other file, in the testing true file here. So all in all, when you're comparing that measurement and predicted, you should know that for various prediction length, right, you're only comparing the predicted sequence, which is however long that future prediction is, to that measurement sequence of the same length instead of the total altogether. So here we are going to give you guys some quick examples of which we already posted on the GitHub of how one might go from saving that data. You can save it for yourself to evaluate different data segments for yourself, to how do you perform the inference, and then lastly to how do you produce that evaluation results, which we provided in terms of the a result rubric rulebook here. So first, let's go to the pretest save MATLAB file, in which, in this case, we're saving for material testing true, we have the original B excitation, we will save the H excitation, the temperature for each of the segment we're saving, and then the full sequence core loss value. And then the second file is the partially provided H segment to you guys. So first, let's go to this file and talk about how, as an example, you can perform this. So as usual, as many of you have seen the format of our MATLAB files, you can do so for many different materials. And then once you have these materials, you will be able to load these, load the window size, which you will decide for your own material. You will have the test length, which is, in our case, 1,000 test points. Now, you can do so for more or less, that's up to you. But for this pre-evaluation, we only provided 1,000 steps here. And then here we have also determined for each segment, for each full sequence, how many number of random segments do we want to select? And then for this many of sequences, how many number of sequences from the same temperature do we want to select? So we want to give it enough variety of different temperatures as well as very random different starting points of a full sequence here. So once you follow this, some material may have 7 frequencies, some may have fewer number of frequencies, and you are going to first load the original data, which we provided you guys. That's the 10 materials of all the training data. You can load those data, and then you can select all the temperature indices where you can select a number of however many numbers of temperature segments you want, however many number of randomly selected indices from each one of the sequence here. And here is the function. The next we go ahead and follow the function of, okay, we can not only do 10%, 50%, and then 90%, you can also vary that in gap to have a different, maybe a 25% predicting 75%, or 20% predicting 80%, any ratio that you want, right? You're setting it here. So once you set that, it's very simple. You simply load the original data, you select the indices, and then you pick that segment of data to save for evaluation. And once you perform all that, you will be able to, you can see that we are able to calculate the all of the original B test segment, the H, the temperature, as well as the loss and the past. Now, in this case, the past, you can see that for any of the future prediction that we have, the future, we set it as the not a number, and this is able to be compatible with the Python code here. So any place you have an NaN, that's where the prediction needs to happen. So you can determine what percentage of data you have based on how much of the NaN you have here. So this will be saved in the testing file padded here, whereas all the rest of the data can be saved in the true data. Now, for the data set we provided to you guys, we actually also provided the original B, the temperature and loss in the padded data as well, just so that you can fact check and make sure everything is synchronized between the two files. So we're only giving you guys a template, an example of how you may be able to perform this. Save the data for yourself, and then perform that pre-evaluation in any ways to test your model. However, for the pre-evaluation that you guys are going to perform, that you can report, that you can simply use the data that we provided to you guys, which is 1,000 time step segments for each one of the materials.
Right. So for the final final test, we actually don't care about the format. We'll give you a CSV file with B and H with padded number. And then all you need to do is to fill up the NAN and then send the CSV back to us. That's all we need for evaluating the performance of the model. And if your predicted results is good, then we will need your code and we'll evaluate, make sure you didn't generate it randomly. Then that's what we're going to do.
Yes.
So we'll
Perfect.
try to make the formatting as simple as possible. We'll give you full, complete training data, and then we'll give you very simple testing data, and you just fill it up and give it back to us.
Yes. Great. So yeah, so that's a template that we give you to you guys. You guys can use it or not to do your own evaluation if you would like to with different data to test the variety of your um, adaptability of your model here. So once you perform that, um, once you get the data, right, you need to perform the inference now, right? And now this inference is where your model comes in. To utilize that data we provide you guys and give us to fill up that NAN gap. So how do you perform this, right? Here we're providing an example of how you would perform the inference. Now, this inference file was a modified version of this was provided in tutorial 1 where we perform that for a full sequence, right? But here now you're doing so for just a segment on any random segments of any possible length of sequence. So here we're providing an example, sort of a template on how you could use your model and perform that inference here. And there are a couple notable things that we would like to go over here. So first, nothing is different. You define your network structure. You can define it in different file. But here we just define it here. The network structure, in this case, is the same as the one I provided in tutorial 1. And then once you pass that, you will have to load the data. Now, for loading the data, one thing that is different now compared to the tutorial 1 is that in tutorial 1, we're using a fixed length, fixed path to predict the entire sequence. But in our case here, we're no longer doing so because you may have a various past memory or past historical segment that you're provided with, and your model will need to adapt to the length of that segment, right? If your memory is, let's say, 1,000 points, but you're provided with only 10 points, well, your model need to adapt to that time step the time step, total time step difference, right? So here we provide an example of, let's say if you have a time step difference in which your total time that your model has is different than what the actual data was provided, then you can perform this data sort of memory, the memory segment manipulation here, where if your length is too long, then you can chop off part of it to retain whatever your model is able to adapt. Or if your data provided is too short, for example, 10%, that is shorter than your memory, then perhaps you need to use your own way of filling up that gap, the empty gap that you may have for you to predict that future, right? So this function is new into how do you perhaps adapt your model to give you that correct ratio sequence to give you that future prediction here. So once you perform that, you'll be able to see that you can still retain the new input of the H, the B, and the next step, and then everything else stays relatively the same here. And once you go into the model training, the model testing, you will see that because we also provide, right, for one single file, we provide 3 different types, 3 different ratios of data. Some of them may be 10-90%, some of them 50-50%, some of them 90-10%. So in our case, how do we determine that? Well, we determine that by when calculating when does the NaN, the not a number value index start. Because for 10%, 90%, all of them should start at a 100 and, for example, in this case, 101 index. But for 50-50, you may start at 501 index. So we determine that by calculating where that NaN stops so that we can segment that out and put them in different category, and then evaluate each one of them, three of them separately. You may evaluate them together, but for our case, in this case, how we performed it is by counting the row index of when that different ratio starts, and then we segment them into different sections, and then we perform the evaluation in our as usual using our model here, right? So these are the two biggest differences that we have for evaluating a segment that has unknown past information, unknown future information, where you need to determine that yourself. So this, all in all, this file should be able to provide you with some clue on how do you adapt that new data of yours into your, adapt your model into that new data and be able to give us that prediction that we would like to have. So all of the data loading are happening here at the bottom, and then you should be able to sort of package your function into a single function here, where at the very end, when we have the final evaluation, you should be able to just provide us with the model, and then we can use the new data to simply put in the BH, the next step B, and some peripheral models or the sampling frequencies to simply give us the result ourselves. So we should be able to run your model in such a way that we can simply use that data, apply it to your model, and then get the result. So make sure to package your model in a very succinct way so that we can simply just run it and then be able to get that for the final evaluation here.
But that's only for winning teams. We're not going to do it
Yes.
for all teams. We'll only need the model for if your result is in a competitive range, maybe like top half of the team. If your result looks great, promising, we'll reach out to you for models.
Yep. Sounds great. So the last thing I want to show is a template on how do you provide that two separate criterias. One is the sequence relative error. One is the energy relative error. So here, once you suppose that you have used the inference file, and you are able to provide, for example, the CSV files for the predicted and the measurement, right? Then you need to load this into, you can use Python or MATLAB or any file. Now, you can load the original data, and you can load the prediction, the predicted file from here. So once you get the CSVs, we should be able to read that prediction and the measurement file, and then we simply can calculate the relative RMSE of the sequences. That's for the H sequences. And then secondly, you can calculate the normalized energy error. Now with this, the core loss is provided, the B is provided, H original is also provided. So with the predicted sequence, you can perform these calculations. And here, we are providing you guys with a code where you're plotting the histogram, which I'll show in the next slide, of both the sequence relative error as well as the energy relative error here. And in this case, you can see we have three cases. The one case is for 10% predicting 90%, one is 50-50, and the third case is 90% predicting 10% here, right? So this simple template should be able to provide you with what you need to provide for the pre-evaluation data, which you will see a format of this in the next slide.
And final test, like we will be happy if you can submit a report with a histogram so that we can quickly identify your error. But if you don't do it, we'll do it ourselves.
Yes.
And in fact, no, final report, they don't have it, right? No, final
Yeah,
report,
they don't have it.
Yeah,
Yeah.
we don't have it.
Yeah.
So we only need your CSV in this case.
Right.
Yeah, the other thing is we don't care about how you train your model. Even if you're winning the challenge, we don't care how you train the model. As long as you can give us the model. So we don't need your code for training the model itself. You can use a random parameter generator if you're able to do it. We don't care. But we will need to evaluate your novelty. If your performance is great, you have to be able to explain the principles of your method. But that will happen.
I
Let me
think
see how.
February maybe
Yeah. So
sometime.
I think, yeah. So I forgot how do we run it last round.
We first evaluate. So once you guys provide the data, so
Right.
the final models, we will evaluate them after January 15th, and
Right.
then we will run through the committee, and then we will determine which model generate results that are great,
Right.
and then
There's
we
a presentation, right? I think there's a
yes,
presentation.
and
Yeah,
then there
we'll
will be a
invite teams to
presentation.
do a presentation, and then the judge committee will come in and then listen to your presentation to evaluate the novelty. I think that's
Yep.
what we're gonna do. Yeah,
Yep.
yeah.
hmm
Good.
hmm Yes. Yes. So, so yeah, so once we provide you guys with these three templates, you may see it to yourself and then see how well, how if you're able to adapt your model in a similar way or in a better way. Now, so to provide the final histogram, right? These histograms on the right here are exactly what how the code that I used shown in the histogram error distribution file. This is how I used to produce it for N87, for example. So as you can see, first we're providing is that the sequence relative error. So let's say here I'm giving a segment of the data that's known and then providing some unknown data. So you can see some um, discrepancies between the predicted and the measurement. And as you can see, if you do this, right, since we provide you guys with around 4,500 or more sequences, you may do so for each one of the segments and then compare the overall sequence relative error and plot them in a histogram as shown here. Now, this histogram, it's only valid for segments of the same length, right? Because if you have a different past past length to predict a different future length, right? You can't do a one-to-one comparison. So for example, here, we're in this example, I'm only cutting it to 700 data points, but I'm using 100 to predict 900 points. So 10% to predict 90%. And so this histogram is the case for all of the data using 10% to predict 90%. So if you're doing so for one material, you will need three different histograms, each one of them for sequence relative error, one of them for 10% predicting 90, one for 50-50, and one for 90-10, which I'll show you in a uh, general format in the next slide here. So once you perform this for the sequence relative error, you should also consider the core loss, right? So the energy loss error, for example, if we have this same predicted segment, and is showing this shaded blue orange here, uh, you should come when we are comparing that discrepancy between the predicted and the measurement, and then we are normalize that against the entire full sequence core loss here. Then you should also be able to provide a histogram, three different histograms for 10%, 90%, 50-50, and 90-10 as well. So all in all, for one material, you should be able to provide around provide six histograms together. So let me show you what that may look like. So all these are provided in our pretest files in the MagNet Challenge 2 folder. So as you can see, if you go to the results, then this is an example template of what the pre-evaluation test may look like. So for example, here for material one, the two materials we're providing here is 3C90 and N87, which you will, if you're providing us with the result, these two are the materials that you will be tested on. So the first material is 3C90. We can see that we have the sequence relative error and then the energy loss relative error, where the sequence error, you have the 10%, 90% prediction, 50-50, and 90-10, right? And then you perform such for the sequence as well as the energy. So you will have six total, six different graphs here. Same thing for the N87. You can also do the same thing and you will generate another six. So for our pre-evaluation, we're only asking you guys to test on two materials. And this is generally what the your result for the pre-evaluation should look like. So that's basically starting from the very beginning of how do you save the data all the way to how do you provide these six files for each of the materials. And if you would like to, there is also the evaluation rule, which we provided in the rule book, where you would also get a sense of what the specific rules are, and you will also be able to access the different files as well as the data itself. For the data, you can access it through the README file here. In terms of data, that will take you to that same Dropbox where we provided you guys with the training data that should be updated with the pretest data. So if you go to that, you will be able to see MagNet Challenge 2 pretest. And if you go into that, for each of the materials, you will see a padded and a true file. And as you can see, the sizes are exactly the same because we provided you guys with the original B temperature loss sequence in both of the files to make sure everything is synchronized. So to access data, this is where you would go. And so this is basically the entire full flow of how you would go from having the data to using your model to predict, adapt to that data you are using to predict the future, and then finally providing that pre-evaluation results. This process is probably basically the same as the final evaluation. And in terms of value evaluation, we will have the data to ourselves and then test it on your model. So I think since we started in May of the first tutorial, you've already provided with the 10 training data. So now you have all 10 training materials. You guys should be able to provide some type of model already for some of the materials. And for this pre-evaluation, we provided you guys with 10 materials of data, but you will only need to provide the evaluation results for two of the materials. In this case, N87 and 3C90. And you will have to do so for all three data splitting scenarios. So if you are providing us with this, this is the format you should provide it in.
Yeah, so again, this is not part of the requirement. Like, we're not requiring you to do this. You can you do it or not doing it. And the result of this evaluation won't change how your final results going to be evaluated. It's just like one additional layer. We hope we can help for you guys to sort of, all right, let's modify our code to test it on two material. So yeah, if you test it on other two material, that's okay, as long as your code are modified so that it's ready for the final testing.
Yes. Yeah. So a notable dates timeline we would like to notify is that the deadline for this pre-evaluation submission, if you would like to, is delayed to postpone to November 15th to give you guys more time for this.
2 months.
Now, if you
yeah,
what's that?
About 2 months from now.
Yeah, 2 months from now. If you would like to submit it anytime, that's fine. 15 is not the final deadline or anything. We can continue to accept your submission if you'd like to have us put you into the system.
No, you don't. They don't even have to submit. I think they can skip this step if they feel confident. But yeah, we will be releasing the 5 unknown data on the same day.
Yep.
November 15th. So
right. Right. So
I don't think we're going to do much. Like, we just look at your report and then, okay, or in other words, we're trying to get a sense of how many teams are still trying to make it.
Right.
That's really just what we're trying to do here.
Yeah. So for the 5 unknown materials we're releasing, they are going to be partial training data provided to you guys. So some of them may have different Each material will have its own scenarios, and you will be only using the training data we provide you guys to perform that, um, to train your model here. And then for the final, we are going to keep some testing data to ourselves, and then we're going to test you guys, evaluate your model based on the testing data here. So you will be provided with the 5 unknown materials training data on November 15th as well. The final submission was originally December 24th. We're postponing that to January 15th to also give you guys more time for the final model submission. And then once you submit the model, we're going to then use the data to evaluate. So these 2 dates are the general milestones for how the MagNet challenge will go all the way till the end of it.
So there are 4 months left, 2 months for final fine-tuning of your methods, and 2 months for applying your method to the new data.
Yeah. Right. Yeah. So with all that being said, that is it from our side. Is there anything you would like to add? Yeah. And does anybody have any questions? Feel free to ask. Raise your hand.
So Shukai, do you want to go to GitHub and then introduce
Sure.
where things are in the
Yeah.
GitHub folder?
Sure. So for the GitHub, if you go to the MagNet Challenge 2, we keep updating the main page here. For the pretest, you will see a pretest different from the tutorials. You go into pretest. Here we're providing you guys with the first the pretest save template. That's the template which we use to help you save that data. The second one is the evaluation, the evaluation of your model, which is in the Python file, the pre-evaluation example here. So you can use this to see how we performed each one of these time step differences, or how do we identify the segment in these categories. And then 3 is the error distribution. This is the template which you will use to plot the histograms, right? And then for any details on the rules, you can read up this PDF here for the pre-evaluation as well as the final evaluation. And then lastly, for the results, this is the result template, which you can use to provide your own. We will also upload a doc version of this so you can modify that and download so you don't have to do this yourself.
Right.
But yes, this is the general file of it. There is also a pretest models. These are the models that I have provided to get these evaluation results for mine own. So these are the models that I have trained for each one of the materials. You can also use that to compare to see how your model compares to mine. Obviously, mine is very rudimentary. You may have a lot more advanced, but that's sort of giving you a sense of, okay, how does mine compare to how our MagNet Challenger 2's baseline
Yeah,
looks
so we
like.
didn't spend too much time optimizing our model. It's sort of working. There are huge room for improvement, and also the way what we're doing here may not work well for the final the new 5 material. So
Yeah,
if your model's performance is not as good as you guys, don't be disappointed. We're not participating in the competition, and
right.
we have way more information than you guys do. And also our method may not work well for the final tests.
Yeah,
So in the final 5 material, the data will be offered in similar way, but we will certainly sample it in different strategy. They are uniformly sampling the entire space. And just like MagNet Challenge 1, we may create gaps in the training data. Like you don't have some of the training data in some of the operating condition, and we are asking you to forecast the material's performance in those areas. So we'll set it up in a way so that for the 5 different materials, we are testing your model from different angle.
right.
But the format are very similar. You should not need to modify your code to read the data, do the training. It's like we factor in what we are interested in when we are creating a training data.
Yeah.
Right.
Yep. Yeah. So yeah, so this is basically the page. We'll also upload the tutorial slides onto the tutorial 5. That will be uploaded here into tutorial 5 here as well. So
Yeah.
you may check that once we upload this.
Yeah.
today's slides.
What is in tutorial 5? So it'll be your
Uh,
slides
that'll
and
simply be my slides. I could also put another copy in the pre-test so people know
yeah, you
what that
can
is
maybe
too.
refer people to the pretest folder
Yep,
for tutorial 5.
sounds great.
Okay,
Yeah.
great.
So yep. Mhm.
Great. Now we can open for discussions. Like we have plenty of time, and many of you may have already have a lot of good experience or even have good models in hand. And any experiences, questions, comments, recommendations?
I think Wilhelm raised his hand.
Okay, let's do it. How do we do it? Answer live. How is the ranking of teams executed when there are 2 metrics and 3 scenarios? I guess the question will be deferred to the judge committee. So we will look at the results together, try to understand. Well, there'll be a presentation, right? So we'll have your ranking based on each of the ranking based on the sequences and collages. And 3 scenarios, we will just lump them together. We will not distinguish the 3 scenarios. In the end, it's just 2 histogram. So we'll show 2 histogram to the judge committee for the 5 material. Each material has 2 histogram, and then they will decide based on there.
Yes.
Right. Let me convert him into a panelist so that we can talk. We'll have. Is there a way we can make everyone?
Yeah, I think we can allow him to
can
talk.
we make can we make everybody?
I can just allow everybody to talk
Yeah,
in the attendees. Yeah, let me allow everybody.
Yeah, Wilhelm, go ahead. Wilhelm, does that answer your question?
Yes, that answers my question.
Yeah. So there will be.
Thanks.
So we are not distinguishing the 3 splits, because the 5 material will be split in different ways, for different purposes. For example, there could be a gap in frequency for the training data. There could be a gap in temperature for the training data. There could be a gap in
The voltage levels,
amplitude, right?
yeah, the amplitude, and then the some of them may have what is it called? Some of them may actually be provided with no previous H at all, maybe
Right.
0%. So it does not have to be 10%, 50. So
Right.
It'll be split differently.
Right. So when you are putting together your code, it's better make it like material agnostic. You will just read a training data set, and then you do whatever you do automatically in the code, and then produce a model. I would say that's probably the most efficient way of structuring your code. Or maybe if you have time, that really depends on what you want to do. If you want to first read the data, understand the data, and adjust your training strategy, that's doable. But for my angle, that's quite a lot of work. So maybe it's better to have a fully automated end-to-end code infrastructure so that you don't have to do anything when the new data arrives.
Okay, and since you are showing histograms, is there some focus on, for example, the 95th quantile or the 50th quantile or something like that?
Yeah, average and 95th.
Average and 95th percentile.
Right.
Okay, thank you.
Yes. Mm-hmm. Great. There's another question. Respected sir, what is the expected accuracy for higher value of H? I mean, in deep saturation region. So the data we provide, some of them will have some deep saturation, but we're not mainly evaluating on any deep saturation region. Most of their data segments are in normal operating range here. So we are not putting emphasis on deep saturation because we simply do not provide data really for deep saturation at all. Some of them have a little bit of saturation, but if your model does not perform well, that's everybody because we're comparing you against all the other teams. So if our data has some saturation, then all the teams will see some saturation. So it's really on if somebody's model may perform a little better with a little bit of saturation, some may not. But since most of the segments are in normal operating range, the saturation range is it's maybe less than 3% of the total segments here.
Yeah, so the data we're going to provide for the 5 new material look very similar to the data you see for the 10 material. And we don't intentionally separate deep saturation or not in our testing or evaluation process. It is what it is.
Yes. I hope that answers your question.
Do we want to make Hero Priya and everybody?
I allowed everybody to
you
speak.
can speak out now. Everybody can speak out.
Mm-hmm.
Any other questions? Comments? Well, we'll just probe it. Like, how many of you guys are still engaged?
Raise a hand. Raise your hand.
do we still have 7? We have 17 members attendee. I'm sure there are some who cannot make the meeting. They're waiting for us. So we have 3 teams. I see.
I saw a total of 5. So
a total of 5. Okay. Okay.
At least there's 5. At least there's 5.
I saw 6. Okay. Well,
yeah.
that gives us some hope. I hope we don't drop below 10 total.
Yeah.
It is complicated, but we're trying our best to make it simple. But it's important. I hope in the end this will be a rewarding experience. Yeah.
Mm. Yeah.
Okay. All right.
Excuse me, one question again. Can you repeat that? So in the test segments, the saturation rate will be so low frequent that the 95th percentile will probably not cover the saturation region. Is that correct?
Yeah, so I think for most of our data, it's not in saturation. When we collect our data, anywhere that sort of reaches a saturation, we cap it out. So any point where the oscilloscope, when we collect that, it goes into saturation, that data point is removed. So most of our data are not in saturation. I believe Hyukjae can correct me if
I think it depends on how you define, right? So
yeah. So what value?
Yeah, that's why we can't say what is saturation, because differentiating saturation itself is a difficult task, and to do it in the right way. So what we can say is that the voltage and current didn't go crazy, because that's where our measurement accuracy cannot be guaranteed as well if your amplitude change across a wide range. Right. So what we can say is single digit below 5%, 3%, 4%. There are chances where the waveform are greatly distorted, but most of the waveform will be sort of look like normal, although the mu may have dropped a little bit.
Yep.
Yeah.
I see. Okay. So you would say the training data is also mostly not in the saturation region, is it?
Correct.
Right.
Yes. Correct.
Okay.
So the testing data will be a sampling. We didn't intentionally sample, except for frequency and temperature and amplitude. We don't handpick the waveforms. We just randomly sample it. Yep. So basically, we're testing more testing. We're doing some extrapolation, but even extrapolation, it's intentionally creating a gap within the full range for extrapolation. It's not, we're asking you, we give you a low frequency and ask you to predict high frequency. No, we give you low frequency and high frequency and ask you to predict the middle frequency. Yeah.
All right.
Yeah. Bingyu, Trey. Are you raising your hands? Yeah.
Hi, Minjae. Hi, Shukai. Thank you so much for the tutorial. So I just have one question. So if I'm not hearing this wrong, you just say that at the final testing phase, which is the deadline on January, we might be anticipating 0% age history data, right?
Yes. One of them, I think one of the material will be 0% data. So then it would really would open up the floor here and say, okay, if you have no memory, just the B excitation, right? How is your model
But actual start from zero. Edge will start from
Okay.
You would assume, yes, you would assume the edge start from 0. Yes.
assume edge start from 0. Yeah. Right.
Yeah.
Okay. Thank you so much for the answer.
Yes. Yes.
So basically, for what we're thinking about it, one material will have just B, and it's startup. It's like one material, you just start from 0 excitation. They give you a B, and then edge start from 0, and then you predict everything.
Yep.
Right.
Right. Anyone else?
Okay, I think that's good enough today, and it's exactly 1 hour. And once we probably will organize another tutorial in 2 weeks or 1 month, once we finalize our testing data. So Shukai will prepare that. We will not release the name of the material, but we can say this is material A, B, C, D, E, and this is how we are going to provide the data.
Yeah.
Yeah.
Yes.
And that'll be a short meeting as we get maybe 2 weeks or 1 month from now.
Yeah.
But our intention is that we don't want you to tailor your model just for how we create the data. But we are happy to share the way we're thinking about it, because that could be a final usage scenario.
Right.
Of the model. So we're looking for a model which is general and multi-purposing, and it's really learning the behavior of the model. Yeah.
Mm-hmm. Right. Cool.
Great. Okay.
All right.
Sounds good. If there's no question, we'll call it end of today's meeting, and wish everybody good luck. And we'll be very happy to engage. Honestly, from our perspective, we feel like we're doing research together with all of you. So we are sort of like a mini research group here. Good communications, actually good. So happy to exchange emails with you guys if you have any questions.
Great.
Great.
Awesome.
Thanks, everyone.
Yeah. Thank you, everybody.
Thanks, Shukai.
Right. Yep. Thank you, Minjin.
Yeah,
Bye-bye. Mm-hmm.
Thank you. Bye.
Bye.
Thank you.